Hello, everybody. I'd first like to thank the organizers of the conference for giving me the opportunity to speak at such a nice conference as this. Um, so as written in my own personalized font up here is I'll be speaking about generalized Sethi-Vafa-Witten formulas. Okay, and I'll start out with a little bit of motivation. Motivated by tadpole cancellation in F-theory, in 1996, Sethi, Vafa, and Witten derived the following formula for the Euler characteristic of an elliptically fibered Calabi-Yau fourfold in Weierstrass form, also known as an E8 elliptic fibration in terms of the Chern classes of its space. And I'm in no way saying that this is the main result of the paper, but simply that this was a formula that appeared inside the paper for the Euler characteristic. 12 C1 times C2 plus 360 C1 cubed, where C1 and C2 are the Chern classes of the base B of the elliptic fibration, where B is a three-dimensional compact, perhaps complex algebraic variety, non-singular. And for those not familiar with the Weierstrass form of an elliptic fibration, I give the explicit equation here. Y squared equals x cubed plus f times x plus g, where f and g are sections of tensor powers of a line bundle L on B. F is a section of L to the fourth, g is a section of L to six, and it's living inside of the P3 bundle, P of O plus L squared plus L cubed. Okay? And this is seems to be the F-theorist's preferred elliptic fibration, as you'll see in most papers on F-theory. And so this is kind of the starting point of my talk. But there are other families of elliptic fibrations as well, admitting different singular fibers than that of a Weierstrass model. For example, E6 elliptic fibrations, E7, and D5 elliptic fibrations. And I've written the equations for convenience up here on the slides. And the E6 and E7 both live in P3 bundles. Well, E7 is in a weighted P3 bundle, P1, 1, 2 of O plus L squared. And the D5 case, the generic fiber is an intersection of two quadric surfaces in P3. And shortly after, Clem, Lian, Rohn, and Yao derived similar formulas for the Euler characteristics of these fibrations as well. And so what you'll often hear in papers on F-theory is that these fibrations aren't necessarily paid that much attention to because the E8 fibration, or all these fibrations, are birationally equivalent to an E8 fibration. But if what you care about is the singular fibers, as most physicists say they do about elliptic fibrations, then when you perform this birational transform of these fibrations to an E8 fibration, you lose a lot of information. I mean, the singular fibers are not preserved under a birational map, and even though the location in the base of the fibration, the location of the singular fibers remains unchanged, the explicit singular fibers themselves are not preserved under a birational map. So if you care about the singular fibers, then just simply saying that all these fibrations are birationally equivalent to a Weierstrass form, yes, it's true, but you're losing a lot of essential information. I mean, for instance, only the singular fibers contribute to the Euler characteristic. And I'm not a physicist, but the singular fibers are where potentially more exotic physics happens as well. And not only that, the E8 fibration that you get from birationally transforming these is singular. So there may be some resolution process involved that you may want to do, which may be hard to globalize, may or may not be hard to globalize. And here you can work with different families of elliptic fibrations from a global perspective right from the get-go that admit different singular fibers. And so as you can see, in the D5 case, if you set all the coefficients at a codimension 5 locus in the base where all the coefficients vanish, you get a fiber that looks like this. 4 P1s all intersecting at a point which is not on the Kodaira list of classification of singular fibers on elliptic surfaces. So there's potentially a lot more interesting things to uncover here in these fibrations, not only for mathematicians, but for physicists as well. And I list the other formulas. I repeat the formula for the E8 case again as well, just to have them all listed here. Okay. And more recently, in 2010, Alufi and Asol showed that these formulas, besides the D5 case, are all merely numerical avatars of more general Chern class identities, which hold over a base of arbitrary dimension and without any Calabi-Yau hypothesis. So I'll quickly go through this theorem. More specifically, let phi from y to b be an elliptic fibration of type E6, E7, or E8, as defined above. And let z be a smooth hypersurface of class g equals 0, as we can see in all the equations. For E6, E7, and the E8 case before, they all have a coefficient g. So z is in the same divisor class as the vanishing of that section of the line bundle. Then the push forward of the Chern class of y is equal to m, an integer multiple of the Chern class of the divisor z in the base, where m equals 4, 3, and 2, respectively, for y of type E6, E7, and E8. And so not only does this theorem encode the different formulas for Euler characteristics of the E6, E7, and E8 fibrations, they work over a base of arbitrary dimension and without any Calabi-Yau hypothesis as well. And just simply integrating both sides of these equations yields the formulas for the Euler characteristics that I stated before. So more specifically, for those not more initiated with these things, once we have the push forward of the Chern class of y, the Euler characteristic y, as is well known, is the integral of the Chern class of y. And integrals are invariant under proper push forwards if you're viewing your Chern classes in the Chow ring. And the last equality comes from the theorem, which is just a multiple of the integral of the Chern class of z. And so the formulas given above for Euler characteristics then fall right out. Okay. So when I was computing these things, when I was computing such push forwards of Chern classes and identifying them with Chern classes of the divisor and the base, there's a couple different standard methods for doing this. And I was kind of wondering if there was a more streamlined way of doing this for producing similar identities of relating push forwards of Chern classes of elliptic fibrations to perhaps Chern classes of divisors in the base, or more generally just elements in the Chow ring of the base. And so I wondered if there was a general scheme for producing such generalized Sethi-Waffle-Witten formulas as the one listed in the theorem previously given on the last slide. So the partial answer is, well, we have a complete answer when the ambient projective bundle is of the form P of O plus direct sums of tensor powers of L. So I admit that this is kind of a restricted class of projective bundles to look at, but all the elliptic fibrations used in physics, at least the ones I've seen so far, are embedded in projective bundles of this form right here. And so the key ingredient for producing such generalized Sethi-Waffle-Witten formulas is a push-forward formula for classes in the Chow ring of a projective bundle. So again, I come from an algebraic geometry background, and for me, Chern classes live in the Chow ring of the projective bundle. And the push-forward corresponds to the proper push-forward of the corresponding Chow rings. So before I list the main result, I'll state the assumptions I'm making here. And so B is any compact, complex, non-singular algebraic variety of any dimension. L is a line bundle on B. We have a vector bundle E, which is a direct sum of tensor powers of L. We can always normalize the first factor to be O. And P of E with canonical projection pi is the associated projectivization. And the main point in the assumption here is this map P. So we have a map P from the Chow ring of the base adjoined an algebraically independent element H to the Chow ring of the projective bundle, given by you take an arbitrary polynomial and you just map it to the pullback of the class in the base to the Chow ring of the projective bundle. And then the powers of H corresponds to C1 of O1 of the projective bundle raised to the corresponding powers of R. So the main point I'm trying to make here is that we can think of classes in the Chow ring of a projective bundle really just nothing more than polynomials in terms of powers of the hyperplane section in the projective bundle. And this is important for the formula that I'll give. Okay? And so this is probably the worst slide of the talk right here, the actual main results, because you can't really appreciate it unless you actually work through the formula in a couple of examples. And so I'll be doing this on the next slide, but for sake of continuity, I'll go through the actual theorem. And with notation and assumptions as above, let C be an arbitrary class in the Chow ring of the projective bundle, and let FC be any polynomial representation of that class. Then the push forward of C is given by this kind of nasty-looking formula with a double summation and QIJs. But the important thing to note here is that this is given in terms of a differential. And so essentially, many Chern classes, or I should say classes in the Chow ring of a projective bundle that you run into in nature, are given in terms of rational functions of pullbacks of classes from the base and h corresponding to C1 of O1. And so you can compute this push forward just by the elementary rules of single variable calculus everyone learns in preschool. And so I'm not going to go through all these, what the m and the n mean, because it won't stick with anyone anyway, so I might as well go to a particular example of applying this formula. So maybe someone can get an appreciation for it. Okay, so the example I'm looking at is let y be a d5 elliptic fibration, as mentioned before. This is, I've been working with these fibrations lately with Mboyo Sol. And so for convenience, I state the equations of y again, and this is sitting inside of a P3 bundle over the base, P of O plus L plus L plus L. The class of y in the Chow ring of the projective bundle is 2h plus 2l squared. And I gave this little commutative diagram for convenience to see what's going on here. But standard exact sequences for the Chern class and then putting it inside the Chow ring of the projective bundle yield that I lower star of the Chern class of y is 1 plus h times 1 plus h plus l cubed plus 2h plus 2l squared all over 1 plus 2h plus 2l squared times the pullback of the Chern class of the base. So the 1 plus h corresponds to the O factor in the projective bundle. The 1 plus h plus l cubed correspond to the three sum ends of L. 2h plus 2l squared corresponds to the class of y. And 1 plus 2h plus 2l squared corresponds to the rank 2 vector bundle on P of E that restricts to the normal bundle of y and P of E. And so by the push forward formula for proper push forwards under phi lower star of the Chern class of y is pi lower star of this class that I've enclosed in parentheses times the Chern class of B. Okay? So computing this push forward under phi star of the Chern class of y really amounts to computing this push forward of this class in the Chow ring of the projective bundle. Okay? So what I'm going to do is I'm going to let C equal this rational expression in H and L. And then by the formula, the nasty formula just given above that involved a double summation and all these double indices and everything, really only involves one term. There actually is no summation involved here. There's only actually one term. So the push forward to C is just 1/2 the second derivative with respect to h of our class C minus a0 plus a1h plus a2h squared all over h, where how do I get a0, a1, and a2? I just plug this into Maple, expand it as a series in h, and my coefficients are a0, a1, and a2. And I simply evaluate this expression at h equals negative L, and out pops this class in the Chow ring of the base right here. Okay? And so from here, I get, by just computing this ordinary differential that we all learn in preschool, we get that the push forward of the Chern class of y is 4L times 3 plus 5L over 1 plus 2L squared times the Chern class of B. Now, the formula didn't turn out as nice as the formula for E6 and E7 and E8, as we saw before, as phi star of C of y with some multiple of some divisor in the base. But it serves the same purpose. I mean, if you want to compute the Euler characteristic or any other invariant in terms of Chern numbers of the associative variety, Chern numbers are invariant under proper push forwards, and you can do it via this same type of formula given right here. Okay, so that's the main example. And then I'll talk a little bit more on this D5 fibration. Just recently, in the past week, Mboyo Sol and I have shown that there exists an orientifold limit of the D5 model at weak coupling, admitting a unique configuration of smooth branes satisfying the F-theory type 2B tadpole matching condition. And so, as I mentioned before, the D5 fibration admits an interesting singular fiber structure, including non-codyral fibers such as this one. And this may lead people to think that this is a very exotic case and that familiar physics can't be extracted from it. But the fact of the matter is we've constructed a weak coupling limit of this vibration, leading to an orientifold picture, a classical orientifold picture with a configuration of smooth branes. And more specifically, this is the tadpole relation that holds. We have that 2 times the Euler characteristic of y times 4 times the Euler characteristic of O, where O is the O7 plane, equals a summation from 1 to 6 of the Euler characteristic of the corresponding D7 branes in the orientifold limit. Yes, we have a weak coupling limit for D5 also. And did I say unique? In terms of a configuration of smooth branes, there's a unique configuration of smooth branes in this limit. So I think in that paper, it was very interesting to note that there was more than one limit for just E8, E7, and I think E8 there was only one limit, but for E7 and E6 fibrations there was there was interesting limits leading to configurations of brains satisfying the tadpole relation. And in this one we get a unique situation here. We have other limits that we have yet to explore, which may lead to configurations of singular brains, but we haven't looked at that yet. I don't have any intuition for that. That's just seems to be the case. Okay, and so this is the specific construction of the weak coupling limit that we've worked on. We let A equal T chi, C equal T eta, where T is our deformation parameter of the fibration. D equals H, E equals phi 1 plus phi 2, and F is phi 1 minus phi 2. So as we let T go to 0, in the flat limit where T actually gets to 0, all the fibers are singular everywhere. And this corresponds to weak coupling in the classical type 2 picture. So the fibers above B minus H equals 0 of the form of two rational curves intersecting transversely at 2 points, and over H equals 0 are of the two rational curves become tangent, and we also get this non-Kodaira fiber over H equals 0 as well. And so the pullback to the double cover X equals B used for the orientifolding of the flat limit of the discriminant as T goes to 0 is this right here. And this is where you compute, where you get the configuration of smooth brains and then check if it satisfies the tadpole relation. So this guy corresponds to the 07 plane. These are 4 D7 brains of the same charge, and these are 2 D7 brains of the same charge. Okay. And so you may be wondering how the generalized Sethi-Vafa-Witten formula or the push-forward formula has to do with this in any way, just besides computing the Euler characteristic. And this is how we, in fact, showed that the configurations of smooth brains is unique. So as has been the case with other weak coupling limits in F-theory, the tadpole relation is obtained from integrating both sides of a much more general Chern class identity, which holds for D5 fibrations over a base of arbitrary dimension and without any Calabi-Yau hypothesis. So this is an important point to note also, that that the physical considerations just predict the relation between the Euler characteristics. But in every case, when the tadpole relation has been shown to hold, the relation between Euler characteristics, the relation has held in a much more general setting. That means what I'm saying is the relation holds at the level of Chern classes over a base B of any dimension and without any Calabi-Yau hypothesis on the elliptic fibration itself as well. Okay? And so the way that the Sethi-Vafa-Witten formula works itself into classifying the smooth brains is that I calculated phi star C of y using the formula, and so 2 times that I think is 2 times 4L times 3 plus 5L over 1 plus 2L squared. Sorry, that should be a plus. And this forms the left-hand side of the tadpole relation, which is fixed. And in the orientifold picture, we have 4 times the orientifold Chern class, which is 2L. Oh, sorry, I'm leaving out C of B. Okay, 2L over 1 plus 2L. Okay, and then I simply have if I let the class of a variable D brain just be AI times L in the base, I can compute the Chern class of a variable D brain such as this, which turns out being 1 plus L over 1 plus 2L. And I know that whatever brains are involved, I know that the summation of AIs has to be equal to 8 because they have to add up to the class of the discriminant locus, and so this becomes a summation 2AIL over 1 plus AIL. So what you can do is kind of solve for the smooth brain satisfying this limit by just taking partitions of the number 8 and plugging them in and see which partitions of the number 8 satisfy this universal identity. So at the end of the day, it's something very simple. But I guess the time for my talk is up now, and I thank everybody for listening and for the opportunity to speak here. Thank you very much. Yes?
So if vibration has a section, can you not always put it in Weierstrass form, not just up to birational transformation?
The D5 vibration limit actually has 4 sections.
Right.
So you can still birationally transform it to a Weierstrass model, but it'll be singular and you'll lose the singular fiber structure. So the non-codirect fibers won't appear, and the two rational curves meeting transversely at 2 points won't appear, and deformations of those as well. You'll just have cusps and nodes.